Welcome back, everybody, for another deep dive. This time we're going to be exploring a recent discovery that's got the physics community buzzing.
Yeah, it's pretty wild.
Yeah.
This research is suggesting we might be seeing quantum mechanics showing up in something we thought we had all figured out.
You're talking about light, right?
Exactly.
Something we all interact with every single day.
And for a long time, physicists have considered light to be purely classical. But this article from the Chinese Society for Optical Engineering just came out this month.
Scientists found a quantum surprise in ordinary light.
That's the one.
What a title. So what are we saying? Is our understanding of light incomplete?
Well, it's certainly making us rethink things.
Okay, so where do we even start with this? Where's the dividing line between, like, the physics of the everyday world and the really out there stuff?
Right, you're talking about the boundary between classical physics and quantum mechanics.
Yeah.
It's always seemed so clear-cut, but now this discovery is blurring those lines.
Okay, so let's break this down a bit more.
Yeah.
What exactly did these researchers find that's got everyone so riled up?
Well, they found evidence of something called quantum coherence, but it's not where we'd expect it.
Quantum coherence. Remind me what that is again?
So it's this idea from quantum mechanics that particles can basically be in multiple states at the same time.
Right.
And they can interfere with each other.
Okay.
Kind of like
Like a wave.
Yeah, exactly. Like waves interfering in a pond.
Okay, I can picture that.
So they create these patterns that classical physics just can't explain.
But I always thought quantum coherence was something that only happened in very specific situations.
Yeah.
Like with entangled photons in a lab setting.
Right. Nobody expected to see it in something like the light coming from your desk lamp.
So are you saying there's quantum weirdness happening in my living room right now?
Well, let's not jump to conclusions.
Okay, fair enough.
This research is super interesting, but it's a bit more nuanced than that.
Okay, so walk me through it. How do they actually find this quantum coherence?
So imagine being able to dissect a beam of light, break it down into tiny little subsystems, and then analyze each one individually.
Wow, so they're looking at light in a whole new way.
Exactly. And to do this, they had to use some pretty cutting-edge tools.
Like what?
Well, one of the key techniques is called photon-number-resolving detection.
So instead of just seeing a stream of light, they can actually count individual photons.
You got it. It's like seeing the individual building blocks of light.
That's incredible. But how does that tell them anything about quantum coherence?
Well, they're not just counting the photons, they're also analyzing a very specific property.
What kind of property?
It's called orbital angular momentum, or OAM for short.
OAM.
It's kind of like a twist in the light wave. Imagine a corkscrew.
So some of these photons are doing a little twist as they travel.
Precisely. And by carefully measuring this OAM along with the number of photons in each subsystem, they were able to find specific subsystems that were behaving in a very quantum way.
So it's not the entire light beam that's quantum. It's like there are these little pockets of quantumness hidden within it.
That's a great way to put it. And finding these two distinct behaviors, the classical coherence and the quantum coherence, is what makes this research so intriguing.
This is definitely blowing my mind a little bit.
I know, right?
Is there any way to visualize this concept of quantum coherence in light?
Sure. Think of it like dropping two pebbles into a still pond.
Okay.
The ripples they create spread out.
Right.
Eventually, they start to overlap. And where the crests of those waves meet, they reinforce each other, creating an even bigger wave.
Where a crest meets a trough.
Exactly. They cancel each other out.
It's like those trippy patterns you get on the surface of the water.
Exactly. And that's kind of what's happening with these photons that are exhibiting quantum coherence.
Their quantum states are like the ripples.
Yeah. They're overlapping and interfering, creating these patterns of constructive and destructive interference, just like the ripples in the pond.
That's a great analogy. But we're talking about photons here, these incredibly tiny particles. How did they manage to isolate and measure them with such precision?
That's where the technology gets really wild.
Okay.
To dive into the specifics of that, though, we'll have to pick this up after a quick...
Okay, so let's talk about the tech. How did they pull off something so precise?
Well, these researchers are working at the cutting edge of optical technology.
Yeah.
They're using equipment most of us have never even heard of.
Give us the rundown.
All right, so remember we were talking about photon-number-resolving detection.
Yeah, being able to count individual photons.
Right, well, that's just one part of the equation.
Okay, so what else are they using?
Another key piece of equipment is called a spatial light modulator.
A spatial what?
Spatial light modulator. It's basically like a really high-tech filter.
A filter for light.
Exactly. But this filter is special. It can actually sort photons based on their orbital angular momentum, that OAM we were talking about.
So it's like a filter that can tell which photons are doing the twist.
You got it. And by combining these two techniques, the photon counting and the OAM sorting, they were able to pinpoint those specific subsystems within the light beam that were exhibiting quantum coherence.
I'm starting to see how they did it, but I have to admit, this OAM thing is still kind of throwing me off.
Yeah, it's a tricky concept.
Why is it so important, this research?
Well, think about it this way. OAM adds a whole new layer of complexity to light.
Okay.
It's not just about the intensity or the color anymore.
It's about the twist.
Exactly. It's about this inherent twist in the light wave. And what these researchers found is that this twist, this OAM, plays a crucial role in how quantum coherence emerges in these light fields.
So it's like this OAM is the secret ingredient that allows these photons to get all quantum on us.
It's a good way to think about it. The OAM is like a key that unlocks this hidden quantum behavior.
All right, I'm starting to wrap my head around it. So we've got this incredible technology that allows us to see light like never before. But why does all this matter?
That's the big question, isn't it?
What are the implications of finding quantum coherence in ordinary light?
Well, one of the most exciting possibilities is in the field of quantum computing.
Quantum computers.
You see, one of the biggest challenges in building these powerful quantum computers is maintaining the coherence of those delicate quantum bits, the qubits.
Right, because any little disturbance can mess them up.
Exactly. And that's why this discovery is so potentially revolutionary.
How so?
If we can learn to harness this natural quantum coherence that exists in ordinary light, it could lead to much more stable qubits.
So we could build quantum computers that are less prone to errors.
Precisely. Imagine quantum computers that are more robust and reliable, that can really tackle those complex problems we've always dreamed of solving.
That would be amazing.
And it's not just quantum computing. This could have a huge impact on quantum communication as well.
Quantum communication.
Oh,
Like sending messages with photons.
exactly. But these messages would be encoded using this inherent quantum coherence.
And what would that do?
Well, it could make those messages virtually unhackable, because any attempt to intercept them would disrupt the coherence and be immediately detectable.
Wow, that sounds like something straight out of a sci-fi movie.
I know, right? And it doesn't stop there. This discovery could also revolutionize sensing technology.
Like what?
Imagine sensors that can detect the tiniest variations in gravity or magnetic fields, or even the presence of single molecules, all thanks to these coherent photons.
That's insane.
It would transform fields like medical diagnostics, environmental monitoring, and even our understanding of the universe itself.
So this is all sounding pretty groundbreaking.
It really is.
But I imagine there's still a lot we don't know.
Of course. We're just scratching the surface here. One of the big challenges now is figuring out exactly how this quantum coherence emerges in these seemingly classical systems.
Because we need to understand the mechanisms behind it.
Exactly. Once we understand how it works, we can start to control and manipulate it, and that's where the real fun begins.
This has definitely been a deep dive into the weird and wonderful world of quantum mechanics.
No doubt about it.
We started with something as familiar as light and ended up exploring these mind-blowing concepts.
Yeah, and what's really fascinating is that this discovery is making us question our understanding of the boundaries between the classical and the quantum.
So to really wrap our heads around that, let's... all right, so we've really gone deep on the technical stuff, but I want to step back for a second and think about what this discovery really means.
Yeah, the bigger picture.
Exactly. This idea that quantum coherence is like hiding in plain sight within ordinary light.
It really challenges the way we think about the world around us.
So how does this change our understanding of physics?
Well, for a long time, we've had these separate categories, right? Classical physics for big stuff and quantum mechanics for the tiny world of particles.
Right, right.
But this discovery suggests that the line between those two worlds isn't as clear as we thought.
So instead of two separate boxes,
Yeah.
it's more like a spectrum.
I like that. A spectrum with classical behavior at one end and quantum behavior at the other.
And somewhere in the middle.
Yeah, somewhere in the middle, they can coexist and even influence each other.
This has to be pretty exciting for physicists.
Yeah.
Like the whole new frontier to explore.
It's a game changer for sure. This research really highlights how interconnected different areas of physics are. We're seeing principles from quantum mechanics showing up in places we never expected.
So maybe there are even more connections out there just waiting to be discovered.
Absolutely. It makes you wonder what other hidden surprises the universe has in store for us.
So what are some of the other areas where this discovery could have an impact?
Well, one area that comes to mind is condensed matter physics.
Condensed matter physics.
Yeah, the study of solids and liquids.
Okay.
These systems are made up of tons of interacting particles, and traditionally we've used classical models to describe how they behave.
Okay.
But this research suggests that quantum effects might be playing a bigger role than we thought, even in these macroscopic systems.
So even in things we can see and touch, there might be this underlying quantum reality.
Exactly. It's a reminder that the universe is full of mysteries, and there's always more to learn.
This deep dive has definitely been a journey. We started with something as simple as light and ended up exploring the complexities of quantum mechanics.
And the potential it has to change the world.
From computing to communication to our understanding of the universe itself.
It's incredible to think about. And for anyone listening out there,
Yeah.
I think the biggest takeaway is to never stop questioning, to always be curious.
Because who knows what amazing discoveries are still out there waiting to be made.
Exactly. Just goes to show that even in the most ordinary of things, there might be extraordinary secrets waiting to be uncovered.
Well said. And on that note, that's a wrap for this deep dive. Thanks for joining us.